All right, today we're going to look at algebraic methods to solve these systems and find the point where the two lines intersect. Now, the issue with graphing is that it's not always precise. For example, if we have fractional intercepts, or if the systems have fractional solutions, it's pretty tough to see exactly what they are using a graph. So therefore we have algebraic methods as well. Now on the quiz you will have to solve a system or two by graphing, but if you do, then I will ensure that the solution will be integers, no fractions. With algebraic methods, all bets are off. They could be fractions, decimals, or they may be integers. So we're going to look at two different methods today for solving these systems. The first one we're going to look at is a method called substitution. Now, substitution is a good method to use when we either have a variable all by itself in one of the equations, or we can easily get the variable by itself. For example, in this second equation in example A, we can get the y by itself pretty easily. We can do that by subtracting 2x from both sides. And then we have a variable that's all by itself. Y is equal to something. Okay? And this line, you should be able to graph that line. The x-intercept would be 4. If we take out the 4y, the x-intercept would turn out to be 4, and the y-intercept would turn out to be 3, and we'd be able to graph that line. In the second line, the x-intercept would be 5. If we took out the y-intercept would be 10 if we took out the x. And the solution we get here would be the point where those two lines intersect. Now, once we have y by itself, we take what y is equal to, the negative 2x plus 10, and we're going to plug that or substitute that in for y in the other equation. That's where the substitution comes in, and that's why this method is called the way it is, called what it is. So when we substitute that in for y, we have 3x plus 4, but instead of 4 times y, we're going to have 4 times what y is equal to. Okay, so we've basically rewritten the top equation, except instead of having y, we have negative 2x plus 10, which is what y is equal to. Now it's just a matter of solving this basic linear equation for x. So to do that, first we distribute the 4. And I'm going to combine some steps here. I'm going to combine the 3x and the negative 8x to get negative 5x. And I'm going to subtract 12 from both sides. And to subtract subtract 40 from both sides. And when I do that, I get negative 28. And to solve this for x, x is equal to 28 fifths. Now, if you'd rather write that as 5.6, you can. I'm okay with that. I'm going to leave it as 28 fifths. I prefer working with fractions. Again, if you leave your answer in decimals, that you need to make sure you're precise. If they turn out to be repeating decimals, make sure you write repeating decimals for that. So I get an answer of 28 fifths for that. And then what I'm going to do, another substitution here. So what I have now is I now have the x-coordinate of that point of intersection. If you write 5.6, that's okay. Still the x-coordinate of that point of intersection. The second part The second substitution that comes in, I'm going to take this 28/5 and substitute it in for x up there. So I know my y-coordinate then would be -2 times 28/5 plus 10. Well, I have -56/5 when I do the multiplication. I need a common denominator, which is 50/5. 10 is equal to 50/5. Now, if you used a decimal, that's okay. You probably have 11.2 plus 10, or I'm sorry, -11.2 plus 10. And in adding these, I have -6/5, or -1.2 for my y-coordinate. And again, just like with the regular linear equations, you can always check to make sure you did it correctly by substituting each of these back in. So 3 times 28/5 would be 84/5. 84/5 plus 4 times -6/5 would be -24/5. So I end up with 60/5, which is in fact equal to 12. We are good there. And then I'm going to check it in the other equation as well. Okay? So the other original equation, 2 times 28/5 is 56/5 plus y is -6/5. So this is 50/5 or 10. Works, so then I know that is the correct solution. Again, you can always check by plugging your solution back into both equations to make sure it works for both of them. So that is the solution. So that is substitution. So that means the point where these two lines intersect is the point 28/5 and -6/5. Now, as you could probably tell, if we tried graphing this system, trying to locate or be specific as far as what fraction or decimal they intersect at would be very tough, which is why we have these algebraic methods to solve these. Now, for B, we will do substitution again. This time, if we look in the top equation, the x is easiest to get by itself. All we have to do is subtract 3y. So x is equal to -3y plus 5. And what we're going to do then is take what x is equal to and substitute it in for x in that second equation. So we're going to rewrite the second equation, but instead of x, we're going to substitute -3y plus 5. That's the substitution, which is why this method is called what it is. So now we have one equation with one variable. Should be very easy to solve. We distribute the -2 first. We combine the like terms here. 6y minus 4y is 2y. We move the 10 by adding it. So 2y equals 5. So y is equal to 5/2. So then that's our y-coordinate of our point of intersection. And again, if you'd rather write 2.5, I am okay with that. Once again, please be precise with your decimals. If you have a repeating decimal, you need to write it as a repeating decimal. But then it gets harder when we substitute it back in. So now, to find the x-coordinate, we're going to plug that 5/2 in for y. So x is equal to -3 times 5/2 plus 5. So that becomes -15/2. 5 is equal to 10/2. Those two are equivalent. So our x-coordinate then is -5/2, or negative 2.5. And once again, to check, you can always plug those back in. So is negative 5 halves plus 3 times 5 halves is 15 halves. So that is 10 halves, which is 5. We're good there. Then for the second part, negative 2 times negative 5 halves is 5. Negative 4 times 5 halves is 10. Negative 10, 5 minus 10 is negative 5. So we know, in fact, that that is our solution. Now, in the next video, we're going to look at a method where it is not very easy to get a variable by itself.